Section 1.5, Inverses of Functions. Part 1, Introduction to Inverse Functions. A function g is the inverse of a function f if g of f of x equals x for all x in the domain of f, and f of g of x equals x for all x in the domain of g. So if the composition, both directions, of g of f of x and f of g of x both equal x, then f and g are inverses. So if such a function g exists, function f is said to be invertible, and function f is also the inverse of function g, so they are inverses of each other. The notation for inverse functions looks like this. So this looks like kind of a -1 power, but it means inverse. So we read this as f inverse of x equals g of x, and g inverse of x equals f of x. A function f is said to be one-to-one if f matches different inputs to different outputs. Equivalently, another way to say that, f is one-to-one if and only if whenever f of c equals f of d, then c equals d. Let's determine if the following functions are one-to-one. So this is a function. All of these examples will be functions. Each x goes to exactly one y. But if I look at these 2 points, I have a point 1, 3 and a point -5, 3. So in this case, the x values are different, but the y values are the same. And this says that if the y values are the same, then the x values also have to be the same. So no, this function is not one-to-one. What about this one? Again, I'm going to look at the points that have the same y values, but they also have the same x values. So according to our definition, if f of c equals f of d, then c does equal d. And in this case, f of c would be f of 1 equals 3. And for this point, the second point, that also says f of 1 equals 3. And 1 does equal 1. So yes, this one is a one-to-one function. Let's look at this example. We have the points 1, 3, 2, -4, -5, -3, and 0, 5. All of the x values are different, so it is a function. And yes, it is a one-to-one function because all the y values are also different. So every x goes to exactly one y, which makes it a function, but also every y comes from only one x. So it is a one-to-one function. The horizontal line test gives us another way to test if a function is one-to-one. A function f is one-to-one if and only if no horizontal line intersects the graph of f more than once. So we call the vertical line test as a way to determine if a graph represents a function. The horizontal line test then is a way to determine if the graph is a one-to-one function. So which of the following are graphs of functions that are one-to-one? Looking at this graph right here, there is no horizontal line that hits the graph more than once. I could draw that horizontal line, it only hits the graph in one spot. This horizontal line only hits the graph in one spot. There is no horizontal line that intersects the graph more than once, so yes, this one is one-to-one. Looking at this function, I can easily see that here's a horizontal line that intersects the graph more than once, so no, this is not a one-to-one function. Looking at this last one, it is also a one-to-one function. I could draw a few horizontal lines, like these two right here, but also the one that looks closest would be this x-axis. It does not intersect either graph at all, let alone the graph more than once. So yes, that one is also one-to-one. Find the inverse of the function f of x equals 3 minus the cube root of x plus 4. So to find an inverse, we're going to follow these steps. We're going to first write this as y equals 3 minus the cube root of x plus 4. And then I'm going to switch my x's and y's and solve for y. So I'm going to write this as x equals 3 minus the cube root of y plus 4. So I switch the x's and y's. Now I'm going to solve for y. So first I'll subtract 3. I get x minus 3 equals negative cube root of y plus 4. Then I'll multiply both sides by that -1 to finish isolating the cube root. So if I multiply the left side by -1, the x becomes negative, the 3 becomes positive, and on the right side I have a positive cube root of y plus 4. Now that I've isolated the cube root, I can raise both sides to the third power, and that gives me 3 minus x cubed equals y plus 4. Then subtract 4, and I get y equals 3 minus x cubed minus 4. So the inverse of f is this function that we have here at the end. So 3 minus x cubed minus 4. That is our inverse of f of x. Note that f is 1-to-1, so it was invertible. F is a cube root function, and if you recall, the cube root function graph looks something like that. So it is a 1-to-1 function, it is invertible, and we found the inverse. Let's expand this inverse, and we'll write our result as a polynomial function with descending powers of x. So to expand this, I have 3 minus x cubed, so 3 minus x times 3 minus x times 3 minus x, and that's all minus 4. So first I'll multiply the first two together, I'll FOIL, so we have 9. Outside and inside are both negative 3x, and last is x squared. Then I still have times the other 3 minus x and a minus 4. Combining like terms, I have 9 minus 6x plus x squared times 3 minus x minus 4. Now I'm going to distribute the 3 from the second parentheses through the first parentheses, and I get 27 minus 18x plus 3x squared. And then I'll distribute the negative x through the first parentheses, and I get negative 9x plus 6x squared minus x cubed. And now I still have that negative 4 at the end. And now I'll combine all my like terms. So x cubed, we have negative x cubed. The x squared, we have 3x squared plus 6x squared gives us 9x squared. The x's, we have negative 18x minus 9x gives us negative 27x. And for the constants, we have 27 minus 4, which is 23. So this is another way to write the inverse of f. Let's find the inverse of this function, f of x equals x squared. Before we can find the inverse, we need to restrict the domain. X squared is not a 1-to-1 function. Here is one example of a horizontal line that intersects the graph more than once, right here and right here. So we're going to restrict the domain, just use part of this function so that we can find the inverse. So one way to restrict that domain would be to choose that x is greater than or equal to 0. And then our graph looks like this. This graph we can see is 1-to-1. It does pass the horizontal line test. So let's do that. Let's find the inverse of y equals x squared when x is greater than or equal to 0. So first we'll switch the x's and y's and then solve for y. Notice if I solve for y, I need to take the square root of both sides, and I get square root of x equals y. Now the reason why we don't have plus or minus square root of x is because our domain says that x is only non-negative numbers, and the square root of a non-negative number is never negative. So we don't need to worry about the plus or minus. We just have y as the square root of x is our inverse of f of x equals x squared when x is greater than or equal to 0. So I can say the inverse of x equals the square root of x.